Don't forget to subscribe and ring that bell.
What an absolutely beautiful day for math. Nay, it is a gorgeous day for calculus. Welcome back if you were with me previously. If you were not, hey, welcome. We are going to continue the 2008 Practice AP Calculus AB exam. Problems 85 through 92. They are the last set of problems for Section 1, Part B. And we get to use a graphing calculator. Nice. If you're in the market for one, I threw links down below. Slew of colors calculators because everybody always asks me what calculator I use. It's a TI-84 Plus CE, the color edition. My classroom set is gray and yellow, so they're boring, but the colors below are pretty sick. And my personal one's the mint green. Yeah, it's minty and it's green. Let's do some calculus. Number 85, the base of a loudspeaker is determined by the two curves, y equals x squared over 10 and y equals negative x squared over 10. For the interval between 1 and 4 inclusive, as shown in the figure above. For this loudspeaker, the cross sections are perpendicular to the x-axis, and they are squares. What is the volume of the loudspeaker in cubic units? My God. Anytime they ask us for volume, we know we need to integrate the area. So the area of what? Well, it's a good thing they told us they're squares. Okay, the area of a square, in case you forgot, is side squared. Okay, so what I need is I just need to figure out what's my side here. Okay, so what's that S value? Let's take a look at the two graphics they give us above. First of all, I think it's really cool that they have that 3D graphic. They don't always do that. And I don't know, I just think it's cool. So let's look at that graphic on the right. And notice, okay, here's my square. See that, the shape? Beautiful. And then as we go further into the speaker, the square kind of gets smaller and smaller and smaller. What we need is the side. Okay, we need this side. Let's look at our graph. That side is represented when I go from the top line down to the bottom line. That's my side. It is the difference from the top function to the bottom function. Notice I use the word difference. Okay, top function is this right here. The bottom function, oh man, it's this one right here. And I said difference. That means subtract, correct? So I'm going to take my top function minus the bottom function. That's going to be the side that I use in my area formula. So let's go ahead and figure that out right quick. The top is x squared over 10 minus the bottom function, which is negative x squared over 10. And whenever I subtract the negative, it just turns to a positive. So this right here is my side. Okay, so when I integrate to find area, okay, to find volume, I integrate the area, excuse me, I square the side. If this is the side, don't forget, I need to square it, okay? That thing right there is what's going into my integration. So let's do this. And it's a great thing that we get to use a calculator. So I'm going to integrate from 1 to 4. They give me that interval, right? My side squared. And my side is x squared over 10 plus x squared over 10. And don't forget, we always need that dummy variable dx. Now look it. You might say to yourself, Visca, I know that x squared over 10 plus x squared over 10 is 2x squared over 10. And you would not be wrong. It is. But when it comes to the calculator, I like to type in everything as it's given to me, math 9. Instead of trying to do something quickly in my head, especially when I get to use a calculator. Why? Because when we try and do things quickly in our head is when we make mistakes. And unless I type it in wrong, the calculator won't make that mistake for me. Okay, so from 1 to 4, parentheses, let's put in our side. So we got x squared over 10 plus, we have another fraction, which is x squared over 10 Boom. And I need to square that. Okay? Because remember, it's the side squared. Dummy variable. Boom. 8.184. That's the volume in cubic units, and that also happens to be choice D. Number 86. Oh, a table. I love graphs and tables and charts. Oh my, I love them, and I start with 2 in a row. 86. The function f is continuous and differentiable on the closed interval from 3 to 7. Continuous means there's no breaks in it. There's no holes. There's no gaps. Differentiable means over that continuous line that I draw, I can take the derivative everywhere. So there's no corner, there's no cusp, there's no vertical tangent line. Because even though these are continuous, I can't take the derivative there. So none of these are in my graph. Okay? This table above gives selected values of f on the interval. Which of the following statements must be true? Don't look at these scenarios here, 1, 2, and 3, and try to find one that it might happen some of the time. Okay? We need to find the one, or maybe it's more than one that's listed, that happens all the time. Yeah, I'm going to draw a little graph here just for visual. Okay? My x's go from 3 to 7. 3, 4, 5, 6, 7. Okay? And all I'm going to do is I'm going to plot some of these points here. Here's 20. Okay, well, why don't we plot them all? Here's 12, and then we have 16, and we have 17, all right? So let's go ahead. 320, that's right here. I'm going to plot 720. That's the same one that's right here. 512 is in the middle. That would be right about here. 417 would be right here. And 616 right here. All I've done is plot those 5 points in the table. Let's take a look at what they give us. The first thing says the minimum value of f. Okay, so when I draw this graph that is one straight line with no breaks, and it doesn't have any corners or cusps or vertical tangent lines, when I draw it, the minimum is 12. Well, the minimum on the table is 12, but I can absolutely draw something that comes down here, comes down even further than comes up. Okay? This point here is lower than 12. All right? So even though this might be true, it doesn't have to 100% be true all the time. Okay? So this is not true every single time, so we label it false. Let's get rid of this. Gone bye-bye. Let's take a look at our choices A through E. I know 1 cannot be in the answer, so A is out. D is out, and E is out. So it's either going to only be 2 or only be 3. Let's look at number 2 now. Do that in green. Right. There exists some value C in between 3 and 7 such that the derivative or the slope is 0. Slope of 0 is a horizontal line this way. Okay? If I connect these dots, no matter how I connect them, I start up here at 20. Yeah? Yeah. I end up here at a y value of 20. And in the middle, at an x value of 5, I'm at 12. So no matter how I connect these dots, I have to come down to here and then come back up here. At some point, I am absolutely going to have a tangent line with a slope of 0. All right, well, Visca, you said I don't have to connect the dots all the time. All right, well, let's get rid of this. Let's bring this red one back in. Boom. Guess what? I have, and I'll do this one in blue, right here, a horizontal tangent line. Okay? It doesn't matter how I draw this. Because I don't have a corner or a cusp, it's differentiable everywhere. At some point, my slope's got to go down, and then it's got to turn to come back up to finish here. So at some point, I have to have a slope that's 0. This number 2 is absolutely true. That means it's choice B. Guys, I'm living life right because the first three problems all have graphs and charts and tables. Yeah, that's how I roll. Number 87. The figure above, the graph of f prime, the derivative of the function of f, on the open interval from -7 to 7. First of all, as soon as I see this, yeah, I get it that it's here. But I always say, okay, y equals f prime. Why do I do that? How come do I do that? How come do I do that? How come I do that? Do I do that all the time? How come? Yes, I do, and I do it for this reason whatsoever. This tells me that no matter what the coordinate is, the y value is always going to be the same as the derivative. And that's going to come into play and help me answer this problem. If f prime has 4 zeros from -7 to 7, how many relative maxima does f have? I don't want to know where it happens. I don't want to know the value of the maximum. I just want to know how many maxes occur. Let's review quickly. In order to find a max, first, I want to know where my first derivative is 0. Okay? That's called a critical point. We'll put a dot right here. It's a critical point. Going to that critical point, I want to have a positive first derivative, which means a positive slope. And then after the critical point, I want a negative first derivative, which means I have a negative slope. So you can see this creates like a little mountain, and that's my maximum. Okay? So the point is, remember a second ago I said y is the same thing as the first derivative? So if I want to figure out my first derivative is 0, that's like saying, well, where the y is 0. If I want to know where the first derivative is positive, that's like saying where the y is positive. And likewise, if I want to know where the first derivative is negative, that's like saying where the y value is negative. So let's look at our chart right now. Let's do this. First thing I want to know, where is my first derivative or y value 0? Anytime I touch the x-axis, my y-coordinate will be 0. If the y is 0, that means my first derivative is also 0. There's 4 of them, and that's fine because in the problem it tells me that there's 4 zeros. All right? So 1, 2, 3, or all 4 of them may have a max. Okay? So I got to look for where my first derivative goes from positive to negative. Here's where it gets fun. Anytime I'm above the x-axis in quadrants 1 or 2, I have a positive y value. If I have a positive y value, that means I have a positive first derivative. Anytime this graph, this green line I'm drawing, that has a positive y value. If it's a positive y value, that means a positive first derivative. Anytime I'm below the x-axis in quadrant 3 or 4, my y-coordinate is negative. That means my first derivative is negative. So any part of the graph that is below the x-axis, I would have a negative y or negative first derivative. So now as I go left to right, we'll do this part in gray. As I go left to right in this graph, let's see what happens to each one of these points. Going this way, I have a negative to a positive. Okay, I don't want negative to positive. Remember, if I look to the right side, I want positive to negative. Okay, so that's not it. That's actually a minimum. Okay, let's keep on going. Let's go to the second blue dot. This is positive. Okay, y value or slope. I hit the 0, but then it maintains being positive. It doesn't change at all. That's not a min or a max. Third dot. I'm going here, being positive, but then I leave negative. Positive to negative is what I want. Positive to negative. Right here, there's a max. Okay, so let's check our last one. Maybe there's 2. Who knows? I'm going to that last blue dot. As I come up to it, it's a negative sign. As I pass it, it's positive. I don't want negative to positive. I want it the other way, positive to negative. So there's only one point where I have a maximum. Choice A. Number 88, finally, just a word problem, no graphics whatsoever. The rate at which water is sprayed onto a field of vegetables is given by R of t. This is nice, because they tell us this is a rate right here. Where T is in minutes and R of T, which is a rate, is in gallons per minute. If it is a rate, we have to have some unit per time. During the interval between 0 and 4 inclusive, what is the average rate of water flow in gallons per minute? Whenever they say average rate, and this is tricky the way they worded it and presented it, whenever they say average rate, I kind of try to train my students to think average rate or average slope is change in y over change in x. However, they already gave me the rate. I want to find the average value of this rate. Okay, I'm given the rate. Okay, anytime I want to find the average value of something, that means I'm going to integrate my function, whatever I'm trying to find the average value of, in this case it's the rate, from the bounds they give me. But in order to make it an average value, I always need to multiply that by 1 over the difference in my bounds. And since we have a calculator, we're just going to plug that right in and hit enter. I like when you get problems like this. Not too much explanation, not too much thought. But it was a little tricky the way they presented that problem with their words. All right, so let's start out by putting our 1 over 4 minus 0, so 1 over the difference in our bounds, times math 9 from 0 to 4. Okay. I've got to put the equation or function that represents my rate, r of t. That is 2 square root of 1 plus 5x cubed, and we need our dummy variable x, otherwise we'll get an error. There it is, 14.691. Sitting beautiful right next to option C. Number 89, another table. The table above gives values of the differentiable functions f and g and their derivatives at x equals 1. If h of x is 2f of x plus 3 times 1 plus g of x, then find h prime of 1. Before I plug in the 1, let's first find the derivative of h, okay? If you don't see it, you best see it or you get it wrong. We are multiplying two things together. We need to use the product rule. The first is 2f of x plus 3, and the second factor is 1 plus g of x. So what does my product rule say? It says, okay, I take my first, just as it is, 2f of x plus 3, times the derivative of my second. Okay, the derivative of 1 is 0. That goes bye-bye. If I don't have an equation to take the derivative of, like a polynomial, where I could use a power rule or whatever, I just have g of x. The derivative of g of x is just written as g prime of x. That's it. First times derivative of the second, plus the second, just as it is, 1 plus g of x, times the derivative of the first, okay? So that coefficient 2 will stay, and it's f prime of x, the derivative of f of x. And then that plus 3, the derivative of 3 goes to 0. All right, this is the derivative of h. I want to throw a 1. They want this at x equals 1. So all of these, oh, I hate to rewrite this, 2 f of 1 plus 3 times g prime of 1 plus 1 plus g of 1 times 2 f prime of 1. All right, let's start putting in values. 2 times f of 1. F of 1 is 3 plus 3. That's 6 plus 3, 9. G prime of 1. Okay, well, that's this one right here. It's 4. Plus Okay, 1 plus g of 1, which is negative 3. That gives us negative 2 times 2 times f prime of 1, which is negative 2. 2 times negative 2, that's negative 4. All right. Do some simple math. You really don't need a calculator here. We got 36 plus, it's 8. 44. We are done. That's like where 44 is, right there. Bam, circle it. You got a 5 on this test so far. Number 90. We have 90, 91, and 92, and we're done. Okay. Number 90 reads, the functions f and g are differentiable. Thank you. For all of x, f of g of x equals x, and g of f of x equals x. This is just a funky way, okay, without using the -1 notation. This is a funky way of just saying that f and g are inverses of each other. Okay, that's just a funky notation. Don't like it, but hey, it is what it is. All right? If f of 3 is 8 and f prime of 3 is 9, what are the values of g of 8 and g prime of 8? Let's do these things one at a time, shall we? Let's start with g of 8. G of 8, okay, is like saying, that's the same thing as saying the inverse of g is f inverse of f of 8, because g is the inverse of f, okay? Okay, so I'm just going to rewrite that. These are the same things, because g is the inverse of f. Okay? So what is this? This is actually rather simple. If I want to find the inverse of f, I got to go back to the original function f. Not inverse, but the original f. They give us f of 3 is 8. The one thing you should absolutely know about inverses are that the x and y's flip. What does that mean? You see how this is the x on the inverse, and we're finding the y? If I go to the original, the x becomes the y. And guess what that means? The x of the original becomes the y of the inverse. So if I want to find the inverse of f at 8, it's 3. And since g is the same thing, that would also be 3. So g of 8 should be 3. Not a third, boom. Not a third, boom. Here we go, 3, 3, 3. All right, so we said we got 2 things to do here. Let's do the next one. Okay, we'll do it in this purple. Why not? G prime of 8. In order to find the derivative of an inverse, and remember, isn't g the inverse of f? Okay, in order to find that, right there, okay, they want the derivative of the inverse. Okay, the derivative of the inverse. All right, I need to find 1 over the derivative of the inverse. Of x. All right. And we just did this right here. We want this at an x value of 8. I just want to really think before I confuse you, right? So this x is going to be an 8. Didn't we just find this value right here? Isn't the inverse of f at 8 equal to 3? It is, friends. So I can take this out and substitute with a 3. 1 over the derivative of f at 3. Okay, because this is 3. We just found it out. Maybe that's why they have you do this first. Now look, is there anywhere that I can find this, the derivative of f at 3? Oh, look, the derivative of f at 3 is 9. So that whole denominator is just 9. All right? So I need to find C, D, or E where it's 1/9. Boom. Yada, yada. Bye-bye, bye-bye. 2 more problems left. Number 91. A particle moves along the x-axis so that its velocity at any time t greater than or equal to 0 is given by v of t equals 5t e raised to the negative t minus 1. Okay? At time 0, the particle's position is 1. Okay? What is the total distance traveled by the particle from time 1 to time, from time 0, I'll be okay, to time 4? All right, well, I mean, they kind of give us a lot of information here, some of which may not be necessary. I personally think they give you this part. Time equals 0, the particle is at position 1, on purpose for you to try and get the equation position, for position rather, and then try and do displacement, where it started and where it ended. But whether it's displacement or total distance, you don't need an equation of position. You can do that by integrating velocity, okay? There's displacement, okay, versus total distance. All right, I'm going to integrate velocity for both of these, okay? Our interval is from 0 to 4, let's not forget. So from 0 to 4, we're going to integrate velocity from 0 to 4, okay? The only difference between the two, because right now they look the same, displacement figures in moving positive to the right and moving negative to the left. So it takes those positives and negatives and combines them. So for displacement here, I want positives, okay, and I want negatives. And I'm going to combine them. But for total distance, I don't care if it's positive, I move to the right, or negative, I move to the left. I still want to count up all that movement. So if I were a human being, for example, which I think I'm a human being, and I step to the right and I step to the left, I don't take the left as negative and the right as positive. I count all those steps as positives and add them up all together. It's like the steps on your watch, your smartwatch, or your phone, okay? If you've got a counter, it doesn't matter if I walk back and forth a million times. I'm going to add them all up and count them individually. So for total displacement, they're all considered positive when I combine them. So how do I do that with total distance? Did I say total displacement? I meant total distance. I use absolute value bars. Because if I have positives and I have negatives, how do I make those negatives into positives? I put it in an absolute value bar. Now it'll turn this into a positive when I combine them. And oh, by the way, if I put positives in an absolute value bar, they'll stay positive. All right? So we're going to take our velocity, which is given to us right here, okay, and I'm going to put it in absolute value bars when I integrate it. So let's go ahead and let's do that right now. Turn this bad boy on. Let's clear this out. We are going to go to Math 9, all right? And my interval was from 0 to 4. Now, we don't really use this that often, the absolute value. So you got to go to Math and move over to Num. Num. And that first thing that says ABS does not stand for anti-lock brake system. It's for absolute value. Boom! And I put in my equation for velocity. 5, I'm going to use an x instead of t. And it is e raised to the negative x. Right? I got to pop off the exponent before I write or type my minus 1. Don't forget the dummy variable. Boom. And if you did that right, you should get, and you can see next to the battery, the yellow light still spinning, that yellow circle, 1.82130. Okay, let's do this. That is approximately 1.82130, yada, yada, yada. Around that 3 decimal places, 1.821, choice D. Okay? The explanation was just to give you an understanding of displacement versus total distance. I can integrate velocity for both, but total distance needs the absolute value. Number 92. Let f be the function with first derivative given by f prime of x equals a sine of x cubed for the interval inclusive between 0 and 2. At what value of x does f attain its maximum value on the closed interval from 0 to 2 inclusive? What value of x? I just need to find the location of the maximum. It's a good thing we have the first derivative because that's what I need to find this. We did a problem earlier, I think it was 87, where they gave us the graph of the first derivative, and we had to find a maximum. But for 92, they don't give us the graph, but so what? They give us the equation, the function. We can just graph that and do the same method, use the same concept. So let me just reiterate this. First derivative where it equals 0, that's called the critical point. That's where all my possible mins and maxes happen. So I want to find some points where my first derivative is 0. On the left of that, I want my first derivative to be positive because that would mean that my function was increasing until I get to this point. And to the right of that, I want my first derivative to be negative because that would mean I would have a decreasing function. And that mountaintop is a beautiful view for a max right there. All right, so that's what I'm looking for on my graph. Let's graph f prime of x, shall we? So here we go. Let's go y equals. We're going to do the sine of x cubed. And by the way, isn't my interval from 0 to 2? It is. So I'm going to change my window from 0 to 2. I don't care about anything else here. And let's, I mean, my y's, it's probably not going to go up and down by 10. Let's pick, I don't know, would 2 work? Let's pick -2 and +2, see if that works. If it doesn't, we can always change that, okay? Let's graph this. Okay, here's f prime of x, which is sine of x cubed. Beautiful. That's really, really good. Okay, it's really good. So let's take this out here and let's do some math, kids, shall we? Let's evaluate and let's interpret this graph. Right now, this graph is f prime. So my y is actually the value of the y for every coordinate is the value of the first derivative. So if I'm trying to find, all right, first of all, where I have critical points, where my first derivative is 0. Well, where's my y 0? My y is 0 right on the x-axis. So that's also where my first derivative is 0, because first derivative is y. So it looks like it happens twice, here and here. All right. So at those 2 points, I want to see, does my first derivative go from positive to negative? Okay. Keeping in mind once again that y is the first derivative. Anytime my y is above the x-axis, I have a positive y value. That would also mean that my first derivative is also positive. And when I'm below the x-axis, my y value is negative. That means my first derivative is also negative. All right? So y's or first derivative are positive anytime I'm above, okay, the x-axis. Right here as well. Let's not forget that. Anytime I'm below the x-axis, my first derivative or y value is negative. So again, as I go left to right, I want to go positive to negative. So let's do this, right? Okay, so as I'm going this way, I'm positive, positive, positive. This is positive. I hit my 0, and then I go negative. Right there is a maximum point. Positive to negative. If I look to the left side of the screen, that's right what I want, positive to negative. The next blue point, as I continue, I start out negative, I hit it, then I go positive. Okay, that's negative to positive. I want positive to negative. So this one is really a minimum. I'm not going to care about that one. So I need to find out, well, this x value is what right here? So I'm going to go back to my calculator, and I'm going to use my intersect function. Or excuse me, I'm going to use my 0 function. Second, trace, and I'm going to pick 0. And I'm going to put this to the left of my 0. That's to the left of it, and hit enter. I'm going to go to the right of it and hit enter. And then hit enter one more time. So you see in my calculator right down here in the bottom left, if I go 3 places, This 4 will round up to a 5. So it's approximately 1.465. All right? This is approximately at 1.465. I see that right here. However, I don't have arrowheads. This doesn't go on forever. What about my endpoints? You better always check your endpoints. So let's do something right here. Okay, let's do a table right now. Here's my x value. If I want to find the original function, I have to integrate my derivative. Okay, and I go from 0 to 2, and here's my 1.465. So let's figure out my y value. It's this column right here. Okay, and how I do that is I always start at 0, okay, because I'm going from 0 to 2, and these are going to end up being my upper bound. So I got to do 3 integrals of my first derivative, and all 3 of them will have a lower bound of 0. But each one of the 3 will have a different upper bound, which is that x-axis. That will give me the original y. Because I can't just plug this value into the equation they gave me. That's the derivative. I don't want to know the slope at that point. I want to know the y value. So I need the original equation, which means I have to integrate my derivative to get the original, all right? First of all, if I throw a 0 in, let's look at this first one. Okay, you know what? This is really just the sine of x cubed, okay? If I throw this in the calculator, if my bounds are the same, I hope you know that's 0, okay? That is a rule. If your bounds are the same, your output is 0 for any integral. Now, you can put it in the calculator if you didn't know that and see that, okay? Let's try the other 2. Let's get out of here, and just for poops and ha-has, let's go math 9. And I'll do 0 to 0 of the sine of x cubed dx. Okay, that should be 0, and it is. Let's try now. Okay, first of all, wait a second. In our x, do we still got that long number? We do. So I'm not going to type it out. I'll type it out, you guys. Math 9. I want from 0 to 1.465 we'll use of the sine of x cubed, bang, dummy variable, x. So that's going to be 0.591. Okay, we're going to round that to a 1, that thousandths place. So let's go here. That's 0.591. All right. Now, if 2 gives me a bigger y value, then it happens at 2 the max. But if this y value is smaller, then my max would occur at an x value of 1.465. Let's go here, and let's go here, hit enter, and I'm just going to go back, and I am just going to change my 1.465 to 2. 0.452. Okay, I'm going to round that to 2. So 0.452. This is a bigger y value, so this is the biggest maximum point that happens at 1.465. That was a lot of work. I mean, you know, if you wouldn't have thought to check the bounds, you would have gotten lucky because it happens to be the answer you would have gotten. Okay? But since 0 and 2 are both options of where that max can occur, I absolutely have to check those endpoints. We are done. I am glad you hung around. This normally takes a little bit longer than other ones, but hey, you know, whatever happens, happens. You know what I'm saying? Like the video, ring the bell, leave a comment, follow me because that's the only way you'll know when I put up future videos. Have a great day and relax a little bit. Take a little nap. Bye-bye.
Don't forget to subscribe and ring that bell.